Alright, this video is probably gonna be a little longer than the others, but it's also one of the more interesting videos and one of the more important ones. So let's jump into the complex plane, modulus, and the arguments of complex numbers. Now, before we do that, let's actually look at the real number line. So the real number line is just the numbers from minus infinity to infinity. And this could be any number you probably have ever thought of before learning about complex numbers. So it could be like 8, it could be pi, it could be Euler's constant, it could be 704, 44, and it could be minus 100. Like all numbers you normally would see or would think about would be here on the real axis. And we're gonna denote these numbers with this double R. All right, what we want to look at in this video is the complex numbers. So let's just go ahead and shrink this a little. So we're gonna resize it and put it over here. All right, as always, we have a complex number C. Let's call it A. It will be equal to A plus I times B as always. Now, I'm just gonna take the time here and write what is the real part. Well, the real part, that's A, and the imaginary part, that's of course B. This is very fundamental, but it's gonna be important in just a second. All right, now let's look at the complex plane. The complex plane is simply a plane where you have two axes. You have one axis here, that is the real axis. So we have the real axis, and then we have the imaginary axis. So this is kind of a way to picture all the complex numbers, because all a complex number really is the real part and the imaginary part. So by two numbers, A and B, we can describe every complex number. Even no matter where it would be in the complex plane, we could describe it by how far should you go out the real axis and how far should you go out the imaginary axis. So let's take an example. Let's say we have a complex number, that is equal to 2 plus 3i. Well, okay, let's look here. We have the real part, so we're gonna go 2 out on the real axis, So that's 1, 2. And for the imaginary axis, we're gonna go 3 out. 1, 2, 3. And then we could just put down our complex number here. So it's this new way of representing complex numbers that's in the complex plane, and we just represent it by where they are in the complex plane. So for example, it would be here, and just like we had the real numbers over here, you can see that if the imaginary part, so if we have the imaginary part equals 0, then you wouldn't go up or down on this axis, and you would simply lie on this axis. So what we see is that the real numbers is actually included in the complex plane, or the complex numbers. So we say that the real numbers is a subset of the complex plane. And if we had to write it in mathematical language, if a number is in the complex plane, then we say it's an element in the complex numbers. And we denote that with, just like we did with a double R here, we use this double C. All right, let's look a little more on this, because what we did here was just go up and take the imaginary part of C, which is of course equal to A, and here we said, it's equal to B, and we said here we take the real part of C, and that is of course equal to A. So that's all we did, and then we put down our complex number in the complex plane. But we would like to find another way to describe this, and this is where we look at modulus and the argument. So modulus is basically just another word for the radius out to the point. So what we would like to find is of course R. Let's just write what we call it. It's modulus, and you can think of it as the radius. And also we want to find theta here, which is the argument, there we go. And theta will be the angle from the real axis up to our radius. All right, but that's all very good, but let's look at how we actually find this. Okay, so the radius or the modulus is equal to also what we call the length of c. So we want to find the length of our complex number c, and our complex number c is up here. Now, the way we do that is simply by looking at the plane here and noticing what we have here is, okay, let me just correct where I put down this, there we go. But what we actually have here is just a triangle with a right angle. So we can use the Pythagorean theorem. And let's just go ahead and do that. So what we could use is that r squared, if we take it here, then we have r squared, that would be equal to, well, one of the sides here is just real part squared, and the other side is the imaginary part squared. So we would say it's the imaginary part of c squared plus the real part of c squared. All right, but in, I think it was video 4, we looked at the complex conjugates, and we saw that that is actually a way to write the imaginary part squared and the real part squared. So what we see is we can simply express the modulus squared as the complex conjugate times the complex number c. And this is of course equal to a squared plus b squared. Now, we are interested in finding just the modulus, so let's just take the square root on both sides, and then we get it's equal to the square root of, we can write it in two ways. Either we can say it's the complex number c times the complex conjugate, or it's simply the square root of the real part squared plus the imaginary part squared. So a squared plus b squared. A squared plus b squared. There we go. And that is how we find the modulus. So let's just put a box around that because it's one of our main results here, together with, of course, introducing the complex plane. But let's also go to the argument. Now, the argument, there's two different ways to do it. Let me just zoom in here on our drawing of the complex plane. Okay, we know our cosine and sine. So let's just look at cosine. And if we remember our Sogator, then we have that this is equal to the adjacent. So adjacent over the hypotenuse. And okay, it's pretty easy here to see the adjacent side. Well, that's just a, because that's just our real part. So we can say that's a divided with, well, what is the hypotenuse? Well, that is just the radius. And we just found a way to find r, so that's no problem. Let's just use r. Perfect. So if we had to isolate for theta, we would just take the inverse of cosine, so we would get r cosine of a over r. Perfect. And we can do the exact same thing for, if we look at sine, then we would have, it's not the adjacent, but it's the opposite. So sine of theta, that would be equal to the opposite over the hypotenuse. And in this case, well, what is the opposite? Well, that's this length, but this length is simply the imaginary part of our complex number, which is b. So we can just write that it's equal to b over, and of course the hypotenuse is still r. And again, we can find theta as arc sine of b over r. But you have to be careful here because, as in all cases, this angle is not unique, because you could also go around here. If you add 2 pi, then you would come back to the exact same place. So when you get your results, you should be a little, or you should be sure that you have the right angle. But if we had to write a formula for this, I would definitely go ahead and then I would look at sine theta over cosine of theta. And it's of course cosine of the argument, even though I'm calling it theta, that's just the Greek letter we use to represent it. All right, but sine over cosine, we know that is just the same as tangents. So, and if we just write, we use what we had here for sine, that was just b over r, we had it here, and cosine is a over r. So what we get is actually, well, we get b over r over a over r. So that's very neat because then the r's cancel, and what we are left with is just b over a. So if you just write that, then we have, it's just tangents of, oh sorry, it's just equal to b over a. Perfect. And now of course we can take the inverse, and then we have a expression for the argument. So the argument is just arctan to, okay, let me just write that a little prettier. So it's arctan to b over a. Perfect. And there we have it, a way to both find the modulus and to find the argument. And all we use to find both the modulus and the argument is simply the real part and the imaginary part of our originally complex number c up here. So I hope this gives an introduction to the complex plane and also to how we find the modulus and the argument. In the next video, we will look at how we actually write this complex number in a way that where we only use the modulus and the argument. So I'll see you in the next video.